Okay, so if we want to talk about distance and some other concepts like between formally, then we need to, we need to set that up with some postulates and go forward from there. Now, of course, we have a couple approaches here. In a purely synthetic approach that David Hilbert did in his work, and which is the approach followed by Greenberg in the textbook, we don't really talk about distance too much, in fact not at all at first, but we do talk about the idea of between, and we take that as an undefined term. So let's take a real quick look at Hilbert's postulates, which are of course the ones that Greenberg is using as well. Now we've already spent some time back in weeks 1 and 2 talking about axioms of incidence. Okay, and you can see those if you review those. But now we're going to talk about some axioms of order, okay, which talk about the concept of between. Okay, so let's just kind of look at those. So postulate, this is set 2 of his postulates. So postulate 2.1 says if a point B lies between a point A and C, then the points A and B and C are 3 distinct points of a line, and B also lies between C and A. Okay, so let's just kind of informally do that over here. If you have a point A and C, let's see, we'll get A, B, and C. So you have points A and C. If B is between A and C, then they are all on the same line. Okay, the same line here, same line AC. Okay, but B is between those two, and the way I do it with Sketchpad, it can actually be the one of those, in which case it's not between. So intuitively, we know what this concept of between means. Okay. But Hilbert is going to take that as an undefined term, and then we're going to just kind of consider what it means. So B is between A and C, but it's also between C and A. So it really doesn't matter which direction you're going here. So that's postulate 2. So it says if it's between, what does between mean? Not really defined, but it does say that they have to be on the same line, and if B is between A and C, then B is also between C and A. So that's the first characteristic. Postulate 2.2 says for 2 points A and C, there will always exist at least one point B on the line AC, such that C lies between A and B. Okay, so if we have a line going through A and C, there's at least one point between them. Now think about what this is going to say. Well, if you pick this point B, then there's also B and A are on the same line, so there's at least one point between them, and at least one point between them, and so forth. And so this is going to lead us to have infinitely many points on a line. So the addition of these postulates here, particularly this postulate 2.2, now means all those cool little finite geometries that we did are no longer going to work. They might have worked for these first 8 up here, but not for this one, this postulate here. Okay. Now the postulates that we've been using, if you notice, are pretty much the same as Euclid. The first set of postulates up here. Some of them are worded just slightly differently, but they're basically the same. But we're not going to take these as axioms down here. We're going to actually prove these things as theorems. The other thing here is of any 3 points on a line, let's say A, B, and C, there does not exist more than one that lies between the other 2. So of these 3, in fact, it'll turn out to be exactly one that lies between the other 2. So B has to be between, one of these is the one that's in the middle, so to speak, so informally. So we're going to actually do this a slightly different way. We're going to, instead of postulating those 3 things, we're going to talk about distance and use our distance to prove those 3 things. Postulate 2.4, let's look at that, and we're going to actually take this one as a postulate as well. Let's get rid of point B here. So we want B this time to be a point not on the line. Okay. So let A, B, and C be 3 points that do not lie on a line, non-collinear set of points. Let A, let's let it be L. Okay. Be a line in the plane which does not meet any of the points A, B, and C. Okay. So here we have a line L. Let's give it let's put it a different color. And let's give it a name. Let's call it L. Okay. So L does not contain A, B, or C. If the line passes through a point of segment AB, okay, it also passes through a point of segment AC or through a segment of BC. Okay, so let's look at this. So here are those three segments. We'll make them red. Okay, so it says if this line goes through any part at all of AB, okay, then, okay, in fact, let's construct it so that it has to go through AB. Let's go back and make it green again, I guess, and call it L again. Okay, so there's L, and the way we've got it done, L has to go through some part of line segment AB. And what this shows is no matter where we move it, it has to go through one or more. It might go through all three. If it goes if it goes through an endpoint, it could possibly go through all three, like that. So it could go through all three sides. It might actually contain a side, like this or like that. Okay. So it might go through AC and not BC. It might go through BC and not AC. It could go through both. Right? And so we have, that's the situation that we're illustrating. Okay? And it turns out we need to take that as a postulate. So we'll action button that for. And I'll tell you what I'm going to do. I'm going to change something here real fast. So we got B. Let me make this. Let me change this to D. Just to make this a little bit better, and I'll change it to D. A, B, D. A, C, D. So change B to D. Okay, so that gives you that. I'm just going to kind of do this so so that in my illustration, when I build it, I can go back and put a point here call B, and I'll use the same illustration for that. Okay, so now I'm going to make a new action button and hide show there. And so that gives me something I can do that, and let's name the action button so this gives us a Euclidean, let's put it, Euclidean illustration of the axioms of order. Okay, and so we have that. Now it also turns out that if you, we'll come back to congruence and parallels later. We also turn out that in Hilbert's approach you need a couple other things down here. You need these axioms of continuity. Postulate 5.1, the Archimedean axiom. If AB and CD are any line segments, then there exists a number n, okay, such that n copies of CD constructed contiguously from A along the ray AB will pass beyond the point B. So what this is saying, so we have, it's saying that we can extend any length that we have, no matter how long the segment AB is. We can line up copies of CD, okay, from A, and just move it on out, and eventually it will get longer than ray AB. It will go on out past B. So this gives us this idea of extending a length a little bit. So this is an Archimedean axiom, so that we can sort of indefinitely extend a length. And then we also have this line completeness postulate, 5.2, that says an extension of a set of points on a line with its order and congruence relations that would preserve the relations existing among the original elements, as well as the fundamental properties of line order and congruence, axioms 1 through 3 and section 1 or sections 1 through 3 and 5.1, okay, is impossible. So what this is going to do is it tells us that these two postulates together are along with the betweenness postulates, are basically going to give us basically the properties of the real numbers. Okay, so in a synthetic approach, we would go, we'd approach it that way. Okay, let's stop there, and we'll come back in the next video to continue.